Why am I reading this? I wouldn't be reading this in any reasonable graduate program, would I? Maybe? I don't know. I'm just here to read, not to criticize anybody's pedagogical practices. Anyway, let's do this. Why graphs? A wide range of problems can be expressed with clarity and precision in the concise pictorial language of graphs. For instance, consider the task of coloring a political map. What is the minimum number of colors needed with the obvious restriction that neighboring countries should have different colors? Yeah, I've heard of that. It's like the minimum coloring problem. I think you can do that with backtracking of some sort. One of the difficulties in attacking this problem is that the map itself, even a stripped down version like figure 3.1a, is usually cluttered with irrelevant information, intricate boundaries, border posts where 3 or more countries meet, open seas, and meandering rivers. Yeah, if you just give something an image of a map, it's gonna be pretty hard. Sorry. So obviously you should simplify it to only the relevant parts. Yes, such distractions are absent from the mathematical object of figure 3.1b, a graph with one vertex for each country. Okay, I think, graph coloring is not the exclusive domain of map designers. I'm gonna be skipping a lot now. Because, I know what graphs are. Some basic operations on graphs arise with such frequency and in such a diversity of contexts that a lot of effort has gone into finding efficient procedures for them. Okay. Formally, a graph is specified by a set of vertices, also called nodes, V, and by edges E between select pairs of vertices. In the map example, V is some integers, and E includes, among many other edges, such sets of integers. So here they're only showing sets of 2, but I'm imagining you can have graphs with edges of 3 or more vertices. You just, I don't know how you would generalize such a thing. Maybe like in the case of 2 vertices, you have maybe like something like a 1. Yeah, like a 1 weight. But then I don't know. Maybe you just have like a bunch of tuples like this. Yeah, I think it's just 2 for now, unless... Actually, I'm curious, but I'll look at it later. Here, an edge between x and y specifically means x shares a border with y. This is a symmetric relation, so yeah. Okay, I know what that means. There's figure 3.1a and b. Fine. Skip. How is a graph represented? We can represent a graph by an adjacency matrix if there are n is the number of vertices in this. This is an n by n array whose ijth entry is 1. If there is an edge from vertex I to vertex j and 0 otherwise. Yeah, and I've seen that before, and I know they don't have to be either 1 or 0. They can be weighted. Any real number. Let's see. The biggest convenience of this format is that the presence of a particular edge can be checked in constant time with just one memory access. I believe that. On the other hand, the matrix takes up O of n squared space, which is wasteful if the graph does not have very many edges. Like if it's a sparse graph, then most of these things will be 0. In which case it might be more efficient to store this in some other form. Therefore, each edge appears in exactly one of the linked lists if the graph is directed, or two of the lists if the graph is undirected. Linked lists? Why linked lists in particular? If, like, and not just lists, or, you know, bidirectional, or just arrays of some sort? I don't know. Maybe I should think about this. Okay, an alternative representation. Adjacency lists. It consists of some linked lists, one per vertex, and the linked list for vertex U holds the names of vertices to which U has an outgoing edge. That is, vertices V for which UV is in the set of edges. Okay, so it's a bunch of linked lists. And each item, each item in a linked list is the outgoing vertices. The vertices that you can go to from this particular vertex. Okay. Total size of the data structure is the number of edges. Checking for a particular edge is no longer constant time because it requires sifting through U's adjacency list. But it's easy to iterate through all neighbors of a vertex. Okay. Yeah. By running down the linked list, and as we shall soon see, this turns out to be a very useful operation in graph algorithms. Again, for undirected graphs, this representation has a symmetry of sorts. V is in U's adjacency list, undirected, if and only if U is in V's adjacency list. How big? Should I read this box here? I think it's talking about like balancing whether you use a matrix or one of those things, depending on how dense the graph is. Depth first search in undirected graphs. Exploring mazes. Depth first search is a surprisingly versatile linear time procedure that reveals a wealth of information about a graph. The most basic question it addresses is what parts of the graph are reachable from a given vertex. Of course, you just start at the vertex, depth first search, and you'll see everything that is connected to that. To understand this task, try putting yourself in the position of a computer that has just been given a new graph, say, in the form of an adjacency list. Each representation offers just one basic operation, finding the neighbors of a vertex. With only this primitive, the reachability problem is rather like exploring a labyrinth. You just start walking from somewhere. You just pick somewhere, start walking, always turn the same direction. Did they talk about figure 3.3 yet? No. Look at it later. Okay. A careless choice of passages might lead you around in circles, or might cause you to overlook some accessible part of the maze. So yeah, you have to remember where you've been. This classic challenge has amused people for centuries. Everybody knows that all you need to explore a labyrinth is a ball of string and a piece of chalk. Yes, the chalk prevents looping. The string always takes you back to the starting place, enabling you to return to passages that you previously saw but did not yet investigate. What are these on a computer? A ball of string is like a stack The chalk is like an array, a Boolean array. Okay. Implicitly via recursion, I mean, that is a stack, though. There's the resulting algorithm is shown in figure 3.3. It's this footnote. I feel like this is something that they'll quiz me on. Some footnote. They would do that. Yeah, this applies to both undirected and directed graphs. In such cases, we adopt the directed notation for edges x, y. If the graph is undirected, then each of its edges should be thought of as existing in both directions, x, y, and y, x. So if it's undirected, then this is not a tuple, but a set. Cool. Now, what did you say about 3.3? The resulting algorithm is 3.3. Explore. Bunch of edges and vertices. The output is visited u is set to true for all nodes u reachable from V. Okay. So it returns the vertices that are connected to V. Yes, start saying that V is visited, and then what this is pre-visit and post-visit. You didn't tell me what those are, did you? These two are optional, meant for performing operations on a vertex when it is first discovered and also when it is being left for the last time. We will soon see some creative uses for them. They're constant, so it doesn't matter if they're here. For each edge in the edges, if not visited. Oh, for each outgoing edge from V, if they're not visited, you explore it. And if there are no outgoing edges, then you don't do this, you just return. Yeah, that is depth first search. But then I saw something weird just now down here. Huh? Oh. Wait, maybe I should look at this. What is this? We need to confirm that explore always works correctly. Now, skip that. Incidentally, this pattern of reasoning arises often in the study of graphs and in essence a streamlined induction. This figure shows the result of running explore on our earlier example graph, starting at node A. Yeah, and breaking ties in alphabetical order. Let me see where that is. 3.4, start A. I don't remember what that graph looked like, but let's read this. This explore visits only a portion of the graph reachable from its starting point, so it's not gonna examine the whole graph. It's not guaranteed to examine the whole graph. We need to restart the procedure elsewhere at some vertex that has not yet been visited. The algorithm of 3.5 called depth first search. Okay, so explore is... It's not depth first search. It's maybe like a part of depth first search. Does this repeatedly until the entire graph has been traversed. The first step in analyzing the running time of DFS is to observe that each vertex is explored just once next to the visited array. During the exploration of a vertex, there are the following steps. Some fixed amount of work. So O of 1 marking it as visited and pre and post visit, which is O of 1, a loop in which adjacent edges are scanned to see whether they lead somewhere new. So that's the number of edges. So is it O of the number of vertices multiplied by the number of edges? No, it is the number of vertices plus the number of edges. But depth first search. For all vertices, mark them false. So initialize an array of falses in the size of the vertices. For all vertices, if not visited, explore it. What? So this explore will mark some as visited, and then you come up. So there's like this O of number of vertices here, and in here there is O of number of vertices, but it's probably not quadratic. Well, maybe they'll just tell me this loop takes a different amount of time for each vertex, so let's consider all vertices together. The total work, yeah, so like if we imagine this whole, let's just read it. Done in step 1 is then O of number of vertices. In step 2, over the course of the entire DFS, each edge is examined exactly twice. Once during explore and once during in step 2. Okay, I believe that. The overall time for step 2 is therefore O of number of edges, and so depth first search has a running time of number of vertices plus number of edges linear in size of its input. This is as efficient as we could possibly hope for, since it takes this long even just to read the adjacency list. Okay, but let me think about why this is not quadratic. If this whole thing were connected, then I would just do this, and it's O of size of V plus size of E. After you do that, it kind of cancels out some stuff in this array here. It's like setting a whole bunch to true, but you still have to read through it. But it's not like for each one here, you do this for each one here, because while you're doing this, you're also kind of doing that. That would convince me. I think I'll just go with that then. Connectivity in undirected graphs. An undirected graph is connected if there's a path between any pair of vertices. The graph of figure 3.6 is not connected because, where's 3.6? For instance, there is no path from A to K. A, K. Yeah. It does have 3 disjoint connected regions corresponding to the following sets of vertices. I believe you. Next, connected components. 3 connected components. Fine. When Explorer started at a particular vertex, it identifies precisely the connected component. Fine. Thus, DFS is trivially adapted to check whether a graph is connected, and more generally to assign each node V an integer identifying the connected component to which it belongs. All it takes is This is an array. Connected component number, I'm guessing that stands for. Okay. I think you can just make that an array. Procedure pre-visit. What is this CC thing? Initialized to 0 and to be incremented each time the DFS procedure calls explore. When you call explore, you increment this counter. What is CC num? Pre-visit. I bet they're going to tell me post-visit later. Yeah. I bet it's when you return from explore, you increment something post-visit. Yeah. We have seen how depth first search a few unassuming lines of code is able to uncover the connectivity structure of an undirected graph in just linear time. But it is far more versatile than this. In order to stretch it further, we will connect a little more information during the exploration process. The times the two important events. Yeah, fine. Revisit. Here's an array. Wait. One way to generate arrays pre and post with these numbers is to define a simple counter clock initially set to 1, which gets updated as follows. Pre-visit v. You assign this counter to the v, the corresponding index in pre, this array, and then you increment it. These timings will soon take on larger significance. Meanwhile, you might have noticed from figure 3.4 that for any nodes, vertices u and v, the two intervals pre-u, post-u, and pre-v, post-v are either disjoint or one is contained within the other. So, that means either none of these are contained in here, or both of them are contained in here, and vice versa. Because it's a stack, basically. Yeah. Depth first search in undirected graphs. Types of edges. Can be run verbatim undirected graphs, taking care to traverse edges only in their prescribed directions. Yes, so directed graphs. Look, what? Tree when vertices are considered in lexicographic order. Why are you showing me this figure? Tree edges are actually part of the DFS forest. What? So that's a tree edge. Something. It's an edge where you go to a vertex for the first time. A back edge is when you look at some place you've already been. A cross edge is it's where you look also where you've already been, but like at the same level of the tree. So you could have gone this way first, and then this way, and you look over here. Forward edges, but why are you looking over here though? Maybe it's like no, you couldn't have gone to D before you go to B. Lead from a node to a non-child descendant in the DFS tree. Okay, so this is actually an edge. You just didn't go here. You went here first. So you could have gone here, gone back, and then gone here, and like looked over here, say, I've already been here, and then go over here. Ancestor and descendant relationships, as well as edge types, can be read off directly from pre and post numbers. Because of the depth first exploration strategy, vertex U is an ancestor of V exactly in those cases where U is discovered first and V is discovered during explore U. Fine. So, what does this mean, U and V? You explore U, you see V, you finish exploring V, you finish exploring U. Or the other way. Or the cross edge. Okay, I see. Directed acyclic graphs, or DAGs. One source, two things for possible. Okay. I'm gonna skip a lot of this. Might regret it. But I know what DAGs are. I know there are different ways to sort them. Strongly connected components. Defining connectivity for directed graphs. Connectivity in undirected graphs is pretty straightforward. A graph that is not connected can be decomposed in a natural and obvious manner into several connected components. Okay. When are you going to talk about this thing? Every directed graph is a DAG of its strongly connected components. If you remove all the loops, remove all the cycles, then you will have a DAG. You have a cycle, just consider that a vertex. And then it's a DAG. I am convinced. An efficient algorithm. The decomposition of a directed graph into its strongly connected components is very informative and useful. It turns out, fortunately, that it can be found in linear time by making further use of depth first search. How do you do that? The algorithm is based on some properties we have already seen, but which we will now pinpoint more closely. 1. If the explore subroutine is started at node U, then it will terminate precisely when all nodes reachable from U have been visited. Okay. Therefore, if we call explore on a node that lies somewhere in a sync, strongly connected component, then we will retrieve exactly that component. I see. If you start exploring inside of a set SEC, then you will never leave it. And so the vertices that you visit will be all of those in the SEC. Figure 3.9 has 2 sync SCCs. Starting explore at node K. Well, let me look at 3.9. Where's K? Is this a strongly connected component? Yes. You start here. You are going to maybe look at this, and end here. And you'll see all of these. 2 sync strongly connected. So yeah, it has to be a sync SCC. Here's one. Oh, here's the metagraph. Okay. This suggests a way of finding one strongly connected component, but still leaves open two major problems. How do we find a node that we know for sure lies in a sink SCC? And, wait, how do we find a node that we know for sure lies in a sink? What if we don't start in a sink? Yeah, so I guess you could start somewhere that isn't in a sink and then end up in a sink. In which case some of those might not be in the sink. And how do we continue once this first component has been discovered? How do you continue once the first sink vertex has been discovered? There is not an easy direct way to pick out a node that is guaranteed to lie in a sink SCC, but there is a way to get a node in a source SCC. So if there is, then you just reverse all the edges. You find a source, you find a sink, right? Reverse all the edges is O of number of edges. A node that receives the highest post number in a DFS must lie in a source SCC. Highest post number. Okay. If C and C prime are strongly connected components, then there is an edge from a node in C to a node in C prime. Whoa, what? These two are SCCs if there is an edge from a node in C to a node in C prime, then the highest post number in C is bigger than the highest post number in C prime. Before I read that proof, I want to think a bit. How about you start in C prime? You aren't guaranteed to have an edge to C. But what if you have an edge to C? You start in C prime. No, because they're different strongly connected components. C and C prime are different. So if there were an edge from... Yeah, so if there were an edge from C prime to C, then this would be the same SCC. Yeah. If the DFS search visits component C before C prime, then clearly all of C and C prime will be traversed before the procedure gets stuck. Therefore, the first node visited in C will have a higher post number than any node in C prime. On the other hand, if C prime gets visited first, then the DFS will get stuck after seeing all of C prime, but before seeing any of C, in which case the property follows immediately. Property 3 can be restated as saying that the strongly connected components can be linearized by arranging them in decreasing order of their highest post numbers. Decreasing order of their highest post numbers. So this would be like following the arrows. If you could like send clones of yourself. Send clones of yourself down the branches. Property 2 helps us find a node in the source strongly connected component of G. However, what we need is a node in the sink component. Our means seem to be the opposite of our needs. But consider the reverse graph. Yeah, that's what I said. All edges reversed. This thing has exactly the same SCCs. Why? Why? If there is a loop, you flip the loop around, it is still a loop. So if we do a DFS search of G reversed, the node with the highest post number will come from a source strongly connected component in GR, which is to say a sink in G. Fine. Yes. Now I forgot what problem B was. How do we continue after the first sink component is identified? Well, what if wait, no. I'll just keep reading. The solution is also provided by property 3. Once we have found the first SCC and deleted it from the graph, find the first SCC and delete it from the graph. The node with the highest post number among those remaining belong to a sink SCC of whatever remains of G. I need to read that again. Found the first SCC. So that's like a source? Or a sink? Delete it from the graph? The node with the highest post number, which you can get in O of size of V, among those remaining belong to a sink. A sink of whatever remains of G. Therefore, we can keep using the post numbering from our initial DFS on G reverse to successively output the second SCC, the third, and so on. The resulting algorithm is this. DFS on G reverse, and yes, so then once you do that, the node with the highest post number must be in a source of GR, which is a sink of G, and then run the undirected connected components algorithm on G, which is just explore, if I remember. I don't remember. And during the DFS, process the vertices in decreasing order from their post numbers. This is linear. I believe you. Okay, I need to see what this is again. 3.2.3. 3.2.3. Nah. I don't know. What are these? Exercise? Okay, there's an example. Let's run this algorithm on the graph of figure 3.9. If step 1 considers vertices in lexicographic order, then the ordering it sets up for the second step is this. 3.9. 3.9. 3.9. I am not convinced, man. Okay. It's too bad I can't click on these. Jump around. Okay, I really need to find this thing. 3.2.3. 3.2.3 is close to here. Okay, it's the one I skipped. These regions are connected components. When explorers started, it will identify precisely the connected components. Okay, I think I see it. So what did you say about this? Okay. After a search on the reverse graph, this will get you the sinks. Or a node that must be in a sink, and then run undirected during the DFS, process the vertices in decreasing order of their post numbers from step 1. Output the second, SCC the third. Okay, so you do this on the vertex, from the vertex with the highest post number. That will get you all of the vertices in that sync SCC. And then you delete those from the graph. And then you start again in a vertex that you haven't deleted with the highest post number. And that'll get you the second SCC, and so on. And it's linear. Okay. Okay. Exercises. DFS on the following graph. Whenever there is a choice of vertices, pick the one that is alphabetically first. Classify each edge as a tree edge or back edge and give the pre and post number. So look at A, look at B, look at C, look at F, look at E. You've already been here. Now we've got some back edges to A and B. Go back to F. I think there's a back edge E to F. No. Undirected, right? And then look at I. And then go back post to F, back post to C, to B, to A. And I wasn't counting, but I could if I wanted to. Then you look at D. How do you know, though? Maybe you look at A, you're done with A, you look at B, you see it's visited, C, you see it's visited, and then you look at D. And then you do this thing. G, H, back edge to D, go back to D. Perform depth first search on each of the following graphs. Yes. This is the same as before. Wait, anything? Oh, they're directed now. Which is fine. I know how to do it. Run DFS based topological ordering on the following graph. Did you tell me how to do that? It's post numbers, right? Yeah. Yeah, it's just post numbers. I'm gonna take a drink. Run the SCC algorithm on the following directed graphs. When doing DFS on the reverse, whenever there is a choice of vertices, always pick the one that is alphabetically first. Okay. So, who is gonna do this? Like on paper? Do you have to like draw one? I guess it's not that bad. I think I'm just whining. Yeah, just draw it yourself. Reverse all the edges. Do DFS. Remember the post numbers. Then start with the node with the highest post number in the original, in this one, and explore that one. And then of those vertices you visited, you kill them. And the edges that connect to them, that lead to them. And then you find the maximum post number vertex that you haven't, that is still in the graph. And then you explore that one. Repeat. And as you're doing that, maybe you just number the SCCs. The reverse is another directed graph on the same vertex set, but with all edges reversed. That is this. Give a linear time algorithm for computing the reverse of a graph in adjacency list format. Okay. So, you have a list of lists. You take the first list. And then you'll see like a bunch of edges that go out from there. And let's see. There's gotta be an efficient way to do this. Memory doesn't matter though, right? Linear time. So that's trivial. Just write them all down, and you're done. Compute. Maybe they want you to present the graph in adjacency list format. In which case, yeah, it's still linear. Just go. So after you've written them all down, you just build your adjacency lists again. What do you do actually? You transpose the matrix. Yep. In and undirected graphs, wait, what? Yeah, transpose is fine. Yeah, vertex, the number of edges. Show that an undirected graph, in an undirected graph, the sum for u in vertices of du is 2 number of edges. Out degree. You want me to prove something? Do it later. Wait, maybe I can just do this now. Use this to show an undirected graph. I don't feel like it. Bipartite graph. Yeah. Whether an undirected graph is bipartite? That's interesting. There are no edges between the vertices in the same set. Yeah, set. Then there's no edge between U and V, huh? You take, for each vertex, you have to go from that vertex to a vertex in the other set. Linear, you just say linear, right? Linear in the number of vertices, and we're done. So just DFS and check, like, you're always going to a different set. There are many other ways to formulate this property. For instance, an undirected graph is bipartite if and only if it can be colored with just two colors. So if you do the coloring algorithm, whatever that is, and you say, hey, we can do this with two colors, then you say yes. Prove this. An undirected graph is bipartite if and only if it contains no cycles of odd length. No cycles of odd length. Well, what if we had a cycle of odd length? Was there one here? No. It would go like here. Yeah. If there were like how should I say this? An odd number is like 2 of some integer plus 1. That plus 1, if it's a cycle, has to go within one set, wherever that plus 1 is. I'm satisfied with that. How many colors are needed to color an undirected graph with exactly one odd length cycle? Color an undirected graph. Not 2. Because you just said that you need at least 3. But do you need more than 3? Do you need 4? No, you don't need 4. I just came up with an example. And that's it. We have 3 containers whose sizes are 10, 7, and 4. Respectively, the 7 and 4 containers start out full of water, but the 10 is initially empty. We are allowed only one type of operation, pouring the contents of one container into another, stopping when only when the source is empty or the destination is full. We want to know whether there is a sequence of pourings that leaves exactly 2 pints in the 7 or 4 pint container. What? Huh. 7 and 4 start out full. I can Okay, I can imagine a graph with this and draw some edges. So there are like 3 vertices, 10, 7, and 4. What does an edge mean? It means you can... how about you just... Okay, not like that. How many... Make this a state. 10, 7, and 4. Just like a 3 vector that represents the amount of water in the 10, 7, and 4 container. And then draw like a state graph, like a discrete finite automaton that has an edge if you can transition from one state to another. That's what I just said. What algorithm could be applied to solve the problem? What was the question? Okay. So we want to find a path from let's say the states are 10, 7, 4. We want to find a path from 0, 7, 4 to anything to anything, or anything to. And all we need to do is explore it, or DFS. So if we even reach one of these, we can say yes. For each node u in an undirected graph, let 2 degree u be the sum of the degrees of u's neighbors. The sum of the degrees of u's neighbors. Undirected. Show how to compute the entire area of 2 degree in linear time. Given a graph in adjacency list format. In addition to collecting the post, why are you even collecting the post numbers? Just don't. Instead, just return the sum. Why do you say 2 degree? The sum of the degrees of u's neighbors. So, nope, that's not gonna work. Just imagine like 3 vertices in a loop. You can say, what is the degree of this? You have an adjacency list. You can see the degree of any particular vertex, but you also want to sum So let's say you explore one, you see that this has a certain degree. So when you go explore one of its neighbors, you give the neighbor that degree. So the neighbor has the degree that it comes from, its adjacency list, you can see, and then you sum the others, which you might get upon their return to you. Yeah, and then when you return, you give whatever to whoever called you this degree. But I feel like I'm missing something here. What if... No, you remember where you've already been in the vanilla DFS, but is that going to cause a problem here? I don't want to spend too much time here. Let's just keep reading. Rewrite the explore procedure so that it is non-recursive. Explicitly use a stack. The calls to pre-visit and post-visit should be positioned so that they have the same effect as in the recursive procedure. Don't call, so don't use recursion. Explicitly use a stack. But, okay, so they're saying if you use recursion that's implicit stack? Yeah, they said that, huh? Okay. So this is easy. You just have some kind of counter and you increment it. But what about this explore thing? Well, if you can still use a stack, you say, I'm exploring vertex V. While exploring vertex V, I see that U I haven't seen before, so I'm going to put U. So first I put vertex V on the stack, and then I put vertex U on the stack, etc. Once I'm done exploring, I pop U, pop V. Once I pop them all, I'm done exploring. And precisely here, once I put something, the first time I see something, I'll increment. So what is this? Push is this, pop is that. Do I do this? Okay, I should say this precisely. I see something. I push it. I pre-visit, increment, assign. Yes, and then I explore it. And then when I'm done, I post-visit, increment, assign, and then pop. Okay. Design a linear time algorithm which, given an undirected graph G and a particular edge E in it, determines whether G has a cycle containing E. Linear time. A particular edge E in it. So it's like a tuple. Determine whether the graph has a cycle containing E. E, you know, let's say E is the tuple UV or VU, right? We just start at U and explore. And if we ever see V, then it has a cycle and it's linear. We're done. Either prove or give a counterexample. If UV is an edge in an undirected graph and during depth first search post U is less than post V, then V is an ancestor of U in the DFS tree. Undirected, this is an edge. During DFS, post of U is less than the post of V. So V should be an ancestor of U. Either prove. Didn't you cite it? But you proved it. Okay. Let's just look at this. V is an ancestor of U, which means you must have explored V, so you must have seen V before you see U. And if that's the case, wait, I think there may be a counterexample. Yep, I came up with the counterexample. So let's say, where's my pen? I forgot to turn it on, but let's say A, V, U. Or U of V, I don't know. See A, let's say this is 1. We see V, pre 2, post 3. Go up to A. And to U, 4, post 5. And then back up to A. So we see 5 and 3. And let's say V is on the right. V is not an ancestor of U. They're siblings. Undirected versus directed connectivity. Prove that in any connected undirected graph G, there's a vertex V in the vertices whose removal leaves G connected. Hint. You should put this hint somewhere else, like in a footnote. Consider it. Okay. Prove that in any connected undirected graph, connected, undirected, there is a vertex whose removal leaves G connected. Okay, let's say there are only 2 vertices. Yes. Wait. Let's say there are 3 vertices. A, B, C. There is a vertex V whose removal leaves G connected. I don't believe that. Let's say ABC is all in a row. You remove B. How is it still connected? Connected. Undirected. Yeah, that's what it is. Oh, there is a vertex. There is a vertex, not like for any vertex. There is a vertex. I gotta read carefully. Give an example of a strongly connected directed graph such that for every V, removing V from G leaves a directed graph that is not strongly connected. Okay. I believe this. I don't feel like proving it. For every vertex, removing V from the graph leaves a directed graph that's not strongly connected. Just give an example. Like a loop. Just a loop. In an undirected graph with two connected components, it is always possible to make a graph connected by adding only one edge. You're just going to tell me that, huh? Give an example of a directed graph with two strongly connected components. Directed graphs, two SCCs, such that no addition of one edge can make the graph strongly connected. Directed graph, two SCCs. Let's say there are two loops. Directed. You just say one edge from one to the other. It's not a strongly connected component because there's no edge going back. The chapter suggests an alternative algorithm for linearization, topological sorting, which repeatedly removes source nodes from the graph. I forgot what that was. Show that this algorithm can be implemented in linear time. But isn't topological sorting linear already? I don't know what I don't remember what they said. Page 97. Of this? Okay. So that wasn't DFS. That was like linearization. You just collect the post numbers and reverse them, and that's your order, topological order. Either prove or give an counter. Wait, did I look at this yet? Yeah. The police department in the city of Computopia has made all streets one way. The mayor contends that there is still a way to drive legally from any intersection in the city to any other intersection. But the opposition is not convinced. A computer program is needed to determine whether the mayor is right. However, the city elections are coming up soon and there's just enough time to run a linear time algorithm. Formulate this problem graph theoretically and explain why it can be solved in linear time. You want me to say whether you can go from any intersection to any other intersection? Linear time, is singular. I am getting off track here, but is I think I know. No, let's read B. Suppose it now turns out that the mayor's original claim is false. She next claims something weaker. If you can start driving from town hall, maybe an intersection, navigating one-way streets, then no matter where you reach, there's always a way to drive legally back to the town hall. Formulate this weaker property as if linear time. So A first. Why? So, what does it mean? It means that there is a path from any vertex to any vertex. Linear time. This is the directed graph because it's all one-way streets. What if you find... No, if you can show that the whole thing is a strongly connected component, then you're done. Can you do that? You just say, you have to reverse it first. It's linear, why not? Just do it. So reverse it, DFS, find the vertex with the highest post number, explore that one in the original graph, and if all vertices are visited, you say yes, otherwise you say no. Okay? Now onto this. If you start from a certain vertex, no matter where you go, there is always a way to go back to that vertex. But then, is this the same thing? Why do they say carefully? Maybe there's a trap. I've been doing this for I want to think about this later. What other exercises are there? There are a lot of graph exercises. Huh? Too sad. I heard something about too sad being SCCs. I think I remember that. That if you see a... You can make this thing a graph. If you see a loop, you have to... If you see a loop, then it's not satisfiable, right? No. If you see a loop... I don't remember precisely, but I know it's something like SCCs. Anyway, I think I'm done reading this chapter. Let's see if there's still anything else. I mean, it's all potentially interesting, but I'm also getting kind of tired. So, take a quick scan through these and yeah, I think I'm gonna end the stream. I said binary relations. By connected components. Equivalence relation. Okay, we're done here.